So today we begin Unit 5, which deals with projectiles, and a projectile is anything that flies through the air influenced only by three things.
Air resistance. Air resistance.
A projectile is anything that flies through the air influenced only by inertia, gravity, and air resistance. Most of the time we get to ignore air resistance because air resistance again only affects objects that are either extremely light or going at very, very high speeds. And most of the stuff that we deal with, air resistance is not a significant factor. So if I'm tossing Bob across the room to you, you don't really worry about air resistance. You worry about, can your arms take it? So, yeah. Here's my rules of determining whether something is a true projectile or not. If the object is self-powered, no. So is a rocket a projectile? No. Is an airplane a projectile? No. They are flying through the air, but they're self-powered. So is a bird a projectile?
No.
Not until you shoot it. So before you shoot it, it's not a projectile. After you shoot it, it is a projectile. And the second rule is, if it flies like a rock, it's a projectile.
So what about?
How many of you have tossed a rock before? Okay, if you tossed a rock, you know what a projectile looks like. If it flies like that, it's a projectile. Yes,
What
sir.
about you shoot out a rocket?
Yes.
So you shoot it out, but it still pushes itself.
Self-powered,
Yeah.
not.
What about the bullet?
So it's
Isn't the bullet?
No, the self-powered,
The gun is one of
it's only getting pushed by the gun. Once it leaves the gun, it's a projectile.
That's fine.
Yeah.
So there's no underwater projectiles, like if you shoot a ball underwater, it's not considered a projectile because it's not in air.
Right.
That's amazing.
But then again, it doesn't go very far.
I mean,
That's fine.
Well, yeah, but
yeah.
There's an air.
Projectiles are typically something flying through the air. So, it's probably called something else underwater. If I throw a cheerleader up in the air, is she a projectile?
Yes.
Yes, she flies like a rock. How about if I toss a football?
Yes.
Yes. What about Larry Boy?
What's that?
Have you thrown Larry
Is he
Boy?
so
Okay.
Larry Boy?
There's Larry Boy.
Yes.
Oh.
Have you thrown?
no.
Yes, many of you don't realize that Larry can
No.
put on a spandex superhero outfit and become Larry Boy. Now, if you've watched him in the silly songs, you probably noticed that he's fairly inept. So, guess what?
He is the protector.
He doesn't have any superpowers. He has super suction ears that don't work very well. But that's it. And then he can change back to regular Larry. Anyway, we're gonna keep him Larry Boy. So if he's Larry Boy, yes, he goes flying through the air, and is he a projectile?
Yes.
Definitely. So how about a frisbee?
Yes.
Yes.
No.
Okay, I didn't bring frisbees because they hurt when you hit them, but these things fly kind of like a frisbee. If I'm tossing one of these around, well, if you don't catch it, it kind of kills it.
should have catched it that time.
Okay. Anyway, again, what are you noticing is happening with these? Yeah, I can get it so that it goes one direction hard. I can get it so that it goes weird. But when I'm tossing these around the room, you should notice that. Do rocks do that? No, I can get these things to go wicked curves. I can have them change direction a couple times. That's not normal for rocks.
So it's so.
So it's not self-powered, but does it fly like a rock?
No.
Okay, so there's something else going on. I don't have to know what that something else is
It's
to
the air.
say it's not a projectile.
It's an air.
Okay, how about a paper airplane? No.
Is that a no?
No.
I can make a paper airplane that loops the loop.
Yeah.
I can make a paper airplane that curves around. I can actually make one that loops the loop and turns around and comes back to me.
You see?
I've never been able to do that with a rock.
Can you make one?
Can you make the plane?
Not right now. We're learning about other stuff right now. We're not doing paper airplanes today.
So it's not a projectile.
So no, paper airplane would not be a projectile. So this would be check, check, check. This would be cross out and cross out. Water balloons.
Yes.
Yes, water balloons fly just like rocks, and they're quite fun to shoot. Bottle rockets.
No.
No, because a bottle rocket is self-powered. Now, once it runs out of juice, does it become a projectile? Yes, so it goes up in the air, and during the part, no, but then afterwards, yes. And in fact, fireworks, when you see fireworks, when they go, do all the little streams look like what rocks travel in?
Yes.
Yes, there's some magic words for that. How about a curveball?
Yes.
Yes.
Curve.
If you curve a rock into the face,
Oh no, you're gonna hit Jerry in the face. Like the president.
Okay, I'm not going to use a baseball because that hurts, and I'm going to use a beach ball because it doesn't hurt when it hits you in the face. But if I take this and I throw it, do you see how that made a big wicked turn?
Yeah.
Do rocks do that?
No.
Okay, so if rocks don't do that, then the answer is always no.
What if you throw the ball like
Okay, we're not talking about what I could do to a rock if I do all sorts of magic special things
No,
to
no.
it. I'm saying when you just toss a rock. That's what we're talking about. Okay, so curveball, frisbee, and paper airplane are not self-powered, but clearly something else is going on in their flights because they don't travel like a rock. So they're not a true projectile. You do not have to understand what the physics is behind why it's not doing projectile stuff. You just have to be able to recognize, hey, it's not. Later we can learn why, but that's later. Okay, now all projectiles are going to travel the same way through the air, and the path that it takes is called a trajectory. So it's a trajectory is the path a projectile takes through the air. And all trajectories have the same shape. It's called a parabola. That's where we have two bolas. This joke there, okay, never mind. So all projectiles are going to travel in parabolic trajectories. This is using all three vocabulary words in one sentence here. This was one, this is two, this is three. So we got all three of our vocabulary words right there. All projectiles travel in parabolic trajectories. So if it's not parabolic, it's not a true projectile. So when you see the firework explode, it goes up, 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 and then.
so cool?
Okay, all of those are little
Parabola.
parabolic trajectories. You say, hey, those little flaming fireballs must be projectiles. Because they are, because they travel in parabolic trajectories. So, yeah. Here I have. Oh, yay. So if I toss this up and it comes back down, is that a parabola?
Yes.
Actually, a straight line up and down is a parabola. It's just got no sidewaysness to it. So if I put a little bit of sideways in, and I put a little more sideways in, and I put a little more sideways in, and if I put a lot more sideways in, those are parabolic. So if I, looks like a palm tree. Thanks. If I draw a nice parabola,
Oh wow. That's so cool.
beautiful, right? Okay, so now I'm going to toss this ball. Does that follow that shape quite nicely?
Yeah.
Hey, what do you know? So the shape that this takes is a parabola. Why do we get this parabola?
Because nothing falls straight down.
We have two different types of motions happening at the same time.
Rising motion.
So what happens, stop it. The parabola forms because we have horizontal motion, and horizontal motion is controlled by inertia, and inertia says we can only travel at a constant speed. Vertical motion is affected by gravity, and gravity makes us go accelerating. So horizontally we want to travel at a constant speed, vertically we want to accelerate. Now if they were both a constant speed or they were both an acceleration, then we would see things travel through the air like bing, bing, And we would say that looks really no, it wouldn't look weird to us because that would look normal to us. But that is weird in our world because it doesn't travel in straight lines like that. It travels in these nice little curves, the parabolic curves. Now the good news is the sideways motion and the up and down motion act independently. Like what we were learning about last week, is that we can break these up into individual components and we can treat the components like they're separate. If I'm going northeast, I'm acting like I'm going north, and I act like I'm going east, and they do work like that. So the good news is if we calculate these separately, the math gets quite simple, whereas parabolic motion is fairly complicated mathematically. Up and down motion is simple, and side to side motion is simple, and they both simply are happening at the same time. So what formulas do I want to use? Well, horizontally, we only have one formula that goes with constant speed motion. So since we only have one formula that goes with constant speed motion, we're going to use that, and that would be d equals vt, or v equals d over t. If I move it up, it's like that. Why did I put little h's there? H stands for horizontal, and this reminds me, I can't stick any d into this formula. I can only stick a displacement that's going sideways into that formula. And I want to make sure that the velocity I put in here is only a sideways velocity. If it's an up and down one, then I don't want to put it in this formula. Similarly, if we're going vertically, we're accelerating, but we're going up and down, so everything's going to be vertical. We are accelerating, and that acceleration is due to gravity. So we already know what our acceleration is. It's going to be g. So we can get away with any of the acceleration formulas that we learn in Unit 2, but the one that we use the most often is the at squared over 2 plus vit. But I changed the a to a g, and I added a couple little v's that stand for vertical, because this is up and down. So again, this is going to be how fast am I going up and down initially, and this is going to be how far up and down did I move. So again, the d stands for displacement, not distance. So if I went up and down and landed at a different height than I took off from, the d is just calculating from start to finish. It's not calculating the distance, it's calculating the displacement. That make sense? Good. And the only thing in common between this formula and this formula is time. The whole time I was going side to side, I was also going up and down the whole time. I'm going up and down, I'm going side to side. So I can solve for time in this equation and stick it here, or I can solve for time in this equation and stick it there. And that's the whole trick for today. It's really easy. If he throws a tennis ball sideways off a building with a 13.2 meters per second velocity, if the building is 4.57 meters tall, how far to the side does the ball hit? So we have our building. This is 4.57 meters. There's Vivi holding her tennis ball. She's throwing the ball how? Sideways. So if it's going sideways, she's shoving it that way at 13.2 meters per second. So that must be my velocity going that way, which is v h. So just like before, we had to label things VI and VF, and now we're going to worry about, is this horizontal or is this vertical? So the thing you want to look for is this up and down, that's vertical. If this is side to side, that's horizontal. So this has to be a duh. But again, is this going up and down or side to side? This is up and down, so this is going to be DV. So it's really important that you label these correctly. If you don't label them correctly, you start just throwing them in anywhere. Of course, when she launches this ball, it's going to travel in a parabolic trajectory down until it hits the ground, and that's what we want to do, is find out how far over to the side. Now, how far is asking for D, to the side is asking for H. So we're saying, well, what is DH? Well, DH, of course, I just learned you that formula.
Velocity horizontal times time.
Is DH times T. So do I know my VH?
Yes.
I do. It's 13.2. And all I need is a time, which I'm going to guess has to be in seconds. So how can I find the time? Well, the whole time it was going sideways, it was also going
Down.
down. So it would be really nice if I had a time down formula. Which we do. Because the whole time it was going sideways, it was falling 4.57 meters. So here's what we're going to do. We're going to take the
13.
d equals gt squared over 2 plus vvit. Now, initially, how fast was I going up and down?
What is that? B1?
Initially, I was going
0.
straight sideways. If I'm going straight sideways, how much up or down am I going? Say nothing.
Nothing.
That makes sense? I'm going straight sideways. I'm not going up or down. I'm just going sideways. So if I'm going straight sideways, then this dv equation is saying, well, how far am I going up and down? And I say, I'm not going up and down at all. So that part goes away.
Why is it VBI?
VVI is initial vertical velocity. Horizontally, since we're going at a constant speed, that's not going to have an initial or a final because it's going to stay the same. But going up and down, it's going to change. So that's what it is initially. Good question. Okay, so if I'm solving this equation for t, this 2 needs to go from the bottom on that side to the top on this side, and g needs to go from the top on this side to the bottom down there, and that's going to give me t squared. So to get rid of the squared, I need to square root, and so this is going to work only when VVI is 0, and VVI is only when 0 when I'm at the highest point going down. So I'm going to call this the t down equation, and so that should remind me, hey, this only works when I'm going down. Now, the biggest problem that people have when using this equation is they're on drugs and not listening. I have a little V here, and what does this V stand for? Vertical. That says it's the vertical displacement. It tells you which D to stick in here, because I might give you a side-to-side D and an up and down D, but we want to put in the up and down D. But what happens is there's always somebody who's doing this wrong because they write it like this. And then they stick the D in there, and then they stick that V in there, and you should only have 2 numbers at the top, not 3. Get it? This is bad, this is good. It's a little v. So don't do it this way. That's bad. Bad, 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 bad. So this is a very handy dandy formula. We'll use it a lot. So we're going to have the square root of 2 times the dv. Now what is my dv?
DV, 4.57.
D stands for what?
Or this.
Displacement, not distance. What does displacement have that distance doesn't? A direction. What direction is it going?
Down.
How do I say down?
Down.
We say down is negative. So we put in a negative 4.57, and then we divide by g, which is negative 9.81. And again, I like to emphasize this because this negative and that negative need to cancel each other out. Otherwise, I'm going to try and take the square root of a negative number, and my calculator is going to say error. And I'm going to say, what's wrong? I can't figure this out. I think I'm doing everything right, and it keeps saying error. So if it says error, make everything positive underneath the radical, and you'll be happy.
So negative 7.
I got 0.965247297. That what you got?
Yes.
Okay, and what do I do with that?
Insert it into the.
That was what I was missing right there.
Yeah.
So I just hit times 13.2. You don't have to erase an answer and then plug it back in. You just leave it there. And that gives me Yeah, this had 3 sig figs, and this had 3 sig figs, and some of you still haven't figured out how to do sig figs because I took a lot of points off your test last time because you just round wherever you feel like it. You should actually look. So 12.7, and again, if this was in seconds, the seconds is going to cancel out the seconds and give me meters, which is a good thing to get for duh.
So it'll be 8 meters.
So apparently Vivi got a good arm. 12.7 meters is how far over the ball bounced. That's pretty easy, right?
So you don't round the times, you just do it like that and then you put it into a calculator.
Well, it's already in the calculator, so you just hit times the other one. Yeah, you don't want to round every stuff, you just want to round when you have next. Okay, Jessica's talking on her cell phone while driving 24.5 meters per second and misses a turn, careens off a cliff, and falls in a parabolic trajectory until her car explodes into a fireball 146 meters from the base of the cliff. How tall was that cliff?
This is why you don't talk on the phone. While you're driving.
There's a moral to this story, yes. You guys are not as good at drivers as you think you are, so keep the eye on the road and you're not going to die.
We're amazing drivers.
That's what you guys all think? And that's why we have 6 accidents in front of school every single day.
So were they my fault?
Yes.
No, they weren't.
She gets her.
So here's Jessica, she's in her little bubble mobile, and her bubble mobile is driving 24.5 meters per second.
Horizontal.
Horizontally, because yeah, cars tend to drive horizontally. If you have a vertical car,
How did you know?
that's pretty special. So that's going to be a VH. Yes, they had, Ford used to have this Edge car, and they had these Edge commercials, and they had it driving up the side of the building, and they had to put a disclaimer on the bottom. Car does not really do this, because they were having people call, I want to get that car. I can drive like Spider-Man. No,
Were you one of those?
I was not one of those people.
Sure.
That's mean. Okay, so 24.5, again, meters per second is the velocity. I'm going straight sideways because that's the way cars go. And of course, she's going to travel in a parabolic trajectory until her car explodes into a fireball. How far?
146.
146 moons over. So this 146 meters, this meter says it's going to be a duh. But what direction is this duh?
Horizontal.
It's horizontal, so this is going to be DH. So I say, hey, I got it made. Now, I'm looking for how tall was the cliff. How tall is dV? So I say to myself, hey, I have a dV formula. And my dV formula was equal to gt squared over 2 plus VVIT. Now, I'm going to give you a hint. Again, I like to start it off easy before we get hard. So today, all we're going to do is roll off tables and fall out windows and roll off cliffs and do something so that our VVI is always
0.
yeah. Next week, when we come back from break, then we'll figure out what happens if we do have a VVI. But for now, we're going to not. So, of course, I know my G. That's easy. G is going to be, and I know my 2. And I know this is, but I don't know what T is.
No.
So now I say, how in the world can I find T? All I know is DH and VH. If only there was an equation that had DH and VH and T in it, this might be useful.
And there is.
Oh, there is. Okay, so the other equation that we learned to, again, we solve this one for time down and plug that time into here, or we can take this information and find time and plug it into here. That's the whole trick. It's not that hard of a trick. It's really quite simple. So if I'm solving for T, the VH needs to move down yonder. So then I say, well, my duh was 146 and my v was 24.5. Which leaves me a t of Very fast. I got 5.959183673. And again, I don't want to retype that thing. All I want to do is hit squared. Because that number was what I was missing right there. So I just square that puppy and then multiply times negative 9.81 and then divide by 2. And I get. Now, what does the negative mean?
Going down.
I am now 174 meters lower than where I started, or Jessica is. So she's buried down here somewhere, and that's 140 or 174 meters lower. Now, I didn't say how far did she fall. I said how tall is the cliff, and we don't measure cliffs from the top down. We measure cliffs from the bottom up. So I would just put this as a positive number. And then put it like that. Super duper simple, right? How many people are going to dominate on this unit?
Yeah.
Good.
I would not forget gravity.
For homework, of course, you want to do?
Or A, B, C, D.
No.
Problem 1?
We've done A and B to death, and so now we're going to do problems 1 and 2. So, yeah. So we're going to do problems 1. I like to keep you guessing.
I can't wait to